All right, let's get this party started. Today we're talking about replacing metal with industrial composites, specifically on the lower volume type production runs. And specifically, we're trying to kind of answer the question, are industrial composite parts suitable to replace many metal parts? And the answer, of course, is yes. I mean, that's why we're doing the presentation, but I want to dig more into the topic, including what industrial composites are exactly, why we use so much metal, and understand that there is a good reason for it, but that we should use those same considerations to consider replacing those metal parts with composites. We'll talk about tips and tricks, some specific examples, workarounds, lots of different ways to use these industrial composites, and then we'll talk very briefly about the ability to print metal if that's what you need. So we'll start by talking about what industrial composites are, and they're not new, right? Composite basically just means that you have a plastic along with some kind of a reinforcement like a glass, like a fiberglass, and you put those two together. Now it could be that this is a chopped fiber, like a fiberglass impregnated plastic injection molded part, like on a lot of these impact drivers and housings, tool housings that you see. They might be individual fiber strands that are wound by these machines, one strand at a time, to create overlapping weaves that then are the perfect shape to the fuselage, such as the case of this Dreamliner, or they're fiber sheets. So it's kind of like a fabric mesh, and then it's impregnated with something like an epoxy. In each of these cases, it's a thermoset or a thermoplastic polymer that is then sort of reinforced internally with this fiber skeleton. So what we're talking about here, though, is none of those processes exactly. This is the additive industrial composite. Markforged additive industrials basically are just extruding out plastic out of a nozzle. The material that's used is generally based on a nylon 6. If you put in a chopped carbon fiber, like the fiberglass on a lot of those tool housings, we call that onyx, and it's probably the bread and butter material. Most everything we do is made out of onyx. We've got other materials coming, like the Ultem, which can be reinforced. The Precise PLA cannot be reinforced. That's not going to be something we're going to consider for replacing production parts. But that onyx material is itself a composite, but we have the ability to reinforce it very much like those other two examples where we're doing sheets or individual fibers, because we are going to be able to individually impregnate continuous filaments of fiber reinforcement, whether that's carbon fiber, fiberglass, which is a little cheaper, Kevlar, or high-strength, high-temp fiberglass. This makes some amazingly durable and resilient parts that are reinforced in ways that are a lot more targeted than really any other material that's been available before. These parts are extremely repeatable across machines. You just basically upload, hit go, and no matter what machine it comes off of, it's going to be perfect. It's going to look fantastic. It's going to be really, really fast and easy to create. So you're going to be able to pull the trigger on a part much faster, iterate faster. You can let this thing run over the weekend, lights out, and it's going to give you a great part when you get back. It's easily scalable in terms of where the reinforcement is created, how much, so you can kind of make it stronger or weaker without having to redesign anything. And the logistics are super simple when you're dealing with spools of plastic and fiber. So when we talk about materials and replacing metal with composites, I was kind of thinking about, well, what are the different materials that we often see when you're building products or building, just about anything? And there's a lot of them there, but nearly all of these materials require some kind of skilled operator to run the machine or to build with that material. It requires some level of special equipment. And then a lot of these require custom molds or tooling. They require sort of a shape to exist before you can then make the part out of that material, right? Fiberglass, wood, you're building these molds and things like that. And that's fine for high volume. Most of these all have a really, really great place to be used to utilize the advantages of each material. But when you're talking about low volume, you cannot amortize the tool. And so building an accurate mold or building an accurate tool would simply be too expensive. And so a lot of times what you end up with is metal is sort of the best available option for you to make that part. And that's generally because of these two technologies, CNC machines and welders. If you've got something in metal and you need to make it, you could probably weld it or machine it or grind it or whatever and build that part, and it'll be strong enough and capable of doing whatever it is that you need to do. And so we just sort of fall into this habit of using metal, specifically steel and aluminum. I think aluminum is probably one of the most popular materials out there. Everybody loves aluminum, but both of these materials are nice and strong. They're extremely tough, so they're not going to crack and break. They've got great stiffness, hardness, surface hardness from abrasion and things like that. They're manufacturable both in an additive and a subtractive method, so you can weld on or you can cut away. Because of the availability of machines and because of the availability of metal fabricators and job shops, your lead times are usually not too bad, but the cost can get up there simply because metal does require either a skilled programmer to program the CNC or a welder to be able to build a suitable part. You've got a lot of flexibility on size when it comes to metal. If you're looking to reduce weight, you can go with different types of metal like aluminum. You can achieve an amazingly great surface finish with metal. It's great for dimensional stability. It handles high temperatures really well. It's electrically conductive so that you can protect the ground circuit. You can do chemical resistance depending on the alloy. Has no problem with UV radiation. Metal does pretty much anything you would want it to do. It's just so powerful and useful and flexible. The problem is it's also extremely strong, so it's kind of hard to work with. When you look at these reasons why we use metal, it's obvious that none of the other categories of materials can meet this set of criteria until you start looking at additive industrial composites. And in fact, a lot of these things that we take advantage of metal for are actually benefits of industrial composites beyond what you would have in metal. And the ones that you don't have the ability to hit, things like hardness, you obviously cannot have an industrial composite that's as hard as a metal. There are ways to work around that. We'll get to that in a second. But let's go into each of these items a little bit deeper and talk about some examples and explain why industrial composites should be seriously considered for almost any part that you would have previously said, no, that's got to be made out of metal, right? It's got to be. I need a part that's strong, tough, and stiff, right? Things like tooling, right? Whether that's brake dies or CMM fixtures, end-of-arm tooling, right? We can't be dropping castings off of the end of our robot end effector. This is really important that these things are strong. But as it turns out, you're going to be able to make your parts as strong or stronger than a lot of metals in the direction that you need, especially when you consider it based on the weight or based on the cost of the material. You can configure the thickness to be whatever you want. You don't have to sort of remove material to make it lighter weight. And you can put in a fiber skeleton that gives you this strength exactly where you need it and when you need it. Now, there are some Z-axis strength considerations between the layers to keep in mind. So it's not as brain-dead simple as an isotropic metal material would be, where it's just strong in all directions. But it's really not that bad. And when you start thinking about things to replace with this part, you would think, well, steel, you can't replace steel with plastic. But we're seeing it happen more and more. People are taking this opportunity to take a steel part or a part that was typically made out of steel and try it on these industrial composites. This is a a machine that previously had a steel die that would form beads on the ends of these aluminum tubes. And that makes sense, right? Your gut says if you're going to form aluminum, you need something stronger than aluminum. Otherwise, it's going to just deform the die. But in this case, these aluminum tubes have absolutely no problem being formed using industrial composite dies. The dies themselves are reinforced with thick fiberglass reinforcement in the areas of compression. So they're plenty strong and stiff. They wear really well. They last a long time. And instead of it being the dies costing hundreds of dollars and taking a few weeks, they're literally costing a few bucks, and they take a couple of hours. You could have a new die ready to go to either replace one that's damaged or that's not functioning, or to accommodate a design that's really challenging, such as these beads that are right up against the formed elbow in these tubes. These can be sort of accommodate just about anything you need in very little time and effort. This is a company called Cobb Tuning. They also use this machine to bend those tubes. And the bottom left corner, you see there's that mandrel, and that is an industrial composite part. It used to be Delrin when they were getting it from the machine manufacturer. But they said, well, wait a minute, what if we built it out of an industrial composite? We would control the method of manufacturing. We could make them stiffer. We could make them softer. We could make them wider. We could make them bend more if needed to get a tighter turn. They would just have a lot more control. And they ended up being cheaper, easier to produce, and would last as long or longer than the Delrin parts they replaced. But there's something that's really cool about this one specifically, and it's the steel dies that are still being used. And I don't know that those steel dies could be replaced, but notice they're leaving tool marks. Anytime you have steel with aluminum or anything that's harder next to anything that's softer, you have the ability or the potential for it to scratch or leave a dent. Whereas with the industrial composites, they're extremely tough and they won't leave a scratch on your aluminum parts. So you may be thinking, well, that's great, but I'm not putting these things in production, right? I might use it on a die that I can throw away and replace, but I'm not going to just use it on something permanent like an overhead lifting mechanism for large castings. But that's exactly what Wärtsilä did. They created and listed with CE a lifting bracket that would safely lift castings in their factory. Now, the previous part that would do this lifting was steel. It was very, very heavy. It was so heavy, in fact, that they would actually have to get the crane to lift the part, to lift the casting, and then they would move the casting, and then they have to use the crane to put the lift back onto the shelf. So they're using a ton of crane time, whereas with this industrial composite, they're able to get the same strength and performance, but it's lightweight, and it crosses the threshold from being too heavy to lift safely by one person to being able something that can be carried around by a person. And so it ends up being a huge time and money saver while also being a superior part. Also, things that are going to have to be certified by regulatory bodies, such as aerospace components. They can now be built using additive manufacturing. Cabin Management Solutions is doing this with their entire production. They're seeing so much flexibility, and because you don't build, 100,000 airplanes, right? You don't generally work with quantities that are super high. You can build all of your production off of a 3D printer in industrial composites. And just like the quality of a Milwaukee impact wrench driver housing, you're going to have absolutely no problems with the strength and longevity of these parts. So you think, okay, great, they're strong. They're capable of doing nearly anything that a metal part might be able to do. But how about delivery? And this is where you really start to differentiate and really start to see benefits of industrial composite, specifically additive, because you've got manufacturability, lead time, and lower cost. So if you've got applications like prototypes of plastic, metal, wood, or anything else, you can build those out of an industrial composite. Vice jaws, fixtures, anything that needs to be customizable, you can build it faster than you can do any kind of tooling. And so what I'm talking about here is building one-off parts or actually planning to build low-volume production parts using industrial composites, because the complexity is free. The design changes are free. You have very low waste because of the way that the filaments and the fiber reinforcements are placed only where they're needed. You don't have a lot of drop. You're not talking about a lot of excess, waste that's cut away by a CNC machine. And so you can prototype metal parts using industrial composites. You may not put these into long-term production, especially like on that top, you've got a bearing housing, right? That's going to mount a bearing to a rotating shaft. That thing probably would not be able to handle high cycles if it was a composite part, but you'd be able to start the machine up and run it confidently with that composite that would give you the same for performance on a testing basis as the metal. And in a lot of cases, we actually see people build parts like that bracket on the bottom, and they say, I'm just going to test it and see how it looks. I just want to put it together to check a few things and kind of make sure it looks okay. And they get it in place and they realize, wait a minute, this thing's more than strong enough. I do not need to go machine this out of aluminum and take that extra cost. This prototype is perfectly suitable for my end use. So if you've got metal parts and you need to prototype, start prototyping early and often. Things like work holding, right? You may just say, well, here I've got a few blocks of aluminum. Let me sit down in the mill for a few hours and I'm going to mill out these jaws that will hold the tubes as I cut them. And the assembly there on the left, notice there's some counterbores, there's some tapped holes, there's probably some slots. You have to tighten some bolts to get it to move the way you want it and hold in place. And it works great. But the one on the right, the industrial composite, has a dovetail groove that you would never try to build on a prototype with maybe like a manual mill. The jaws are movable, they're replaceable, right? You can pop them in and out. These actually have embedded magnets on them and stops on each side so that the thing can snap on and off in an instant. And there's also no hardware required to be able to build it, simply because of the complexity and the undercutability that you can do on a printer. Now, if you're thinking, okay, great, I can make it quickly, it's strong, but I need it to be a really high quality part, right? I want it to have a nice surface finish. I want it to be perfect dimension. I want it to have chemical resistance, UV resistance, whatever. No problem. This is great for building customer samples, work holding on CMM or CNC machines, or anything that a human has to hold it. You can build a part that's not going to be sharp. You can hold it in your hand. It's not going to be overly rough. And depending on what you're doing, it's actually going to make a really superior part. So for things like CNC or CMM work holding, these things are absolutely great. You can build exactly what you need instead of trying to sort of use an erector set and a bunch of generic pieces to try to hold the part down. You can make something that matches your part exactly, holds it precisely where you want it, and is built to relocate that part over and over and over again without a whole bunch of tooling or without a whole bunch of effort, which is exactly the kind of thing you need for CMM. At the top right, that is a tray that's built to hold parts in a laser engraver. And not only because of the flexibility of the shape, not only does it hold the part in exactly the right place and make sure it holds it very securely and carefully, but you can also customize the bottom of that thing to snap into place into your machine so it's a repeatable, easy to remove and easy to install component. So when you think about fixturing, if you think about work holding, you think, yeah, I can't, fix these out or change these out because it would be really hard to put them back in the exact same spot or something like that. Start looking at these industrial composite parts. That plate on the bottom of that left work holding piece, that's actually an industrial composite with embedded hardware, embedded nuts. So you have steel threads inside there that you can repeatedly clamp down to on that high tolerance composite part. If you start talking about end-use parts, we generally will show you these Markforged Onyx parts, these industrial composite parts, exactly how they look coming off the machine, because they look sexy, they look beautiful, or at least we think so, right? They give you a really nice clean surface finish with no after processing required. But that doesn't mean that you can't paint over it, doesn't mean you can't sand it. And in fact, on the bottom right corner, look at that. That is a chrome-plated Onyx 3D printed part. That thing's going on an airplane. It's rated for that, and it's absolutely beautiful. So your parts don't have to look like 3D printed parts, but those 3D printed parts are not going to be out of place in an industrial environment or in the hands of your customers or your employees. Now, I'm going to make one specific plea about aluminum. When we introduced our metal printer, the Metal X, we had so many people say, hey, I want to do aluminum. And my answer to that is, why? What is it about aluminum? Is it that list we talked about earlier about how strong, manufacturable, and everything else it is? Because if that's the case, the industrial composite has probably got better benefits across the board than that aluminum part. So almost anything that you can make with aluminum, you could probably replace with an industrial composite. And it's probably not even close. It's pretty unbelievable to see just exactly how powerful these are. And a lot of times you don't actually need strength across the entire part. You only need strength in certain areas. You can reinforce only those areas. You can build a part that has a higher strength to weight ratio than aluminum, and you'd actually save a ton of money by not reinforcing every little area along the part like you'd have to if you were building the part out of a single chunk of aluminum or assembling it from multiple pieces. Let's say you do have an application that requires something like a hardened steel pin or a hardened steel bushing or an oil impregnated brass bushing or bearing or steel insert or something like that. That's where you can still get a lot of benefit from an industrial composite part, but then create what we call a hybrid part where it uses some small metal piece. That could be the jaws of the wrench are made of metal, or it could be that the insert or the head of the hammer is made out of metal. And if you think about just about any standard hammer, that's a hybrid part too, right? It's a wood or fiberglass handle with a metal head. In this case, this is a dead blow hammer that I built. And if you didn't know, dead blow hammers have metal inside them, but they have plastic on the outside. In this case, this is all plastic, but with a metal insert for the dead blow shot, and one side face has metal so that I can hit something sharp without it damaging my dead blow hammer. So it's amazing what you can do with these industrial composites when you think about how powerful they are and how ubiquitous they already are, but they just simply have gotten so much easier to fabricate with the additive manufacturing. Now, there are really hard stops where you can't go beyond that and use composites. If you're talking about anything above the boiling temperature of water, if you're going to have fire or something like that, you're not going to be able to use Onyx at those sustained high temperatures. Temporary high temperatures like this welding jig are no problem. If you need a ground connection to be able to case ground your electromechanical components, you need them to be metal. If you're going to have super high intensity loading, high cycle loading, if you need super high surface finish requirements, those all will generally require metal. Although there are some times where that surface finish requirement goes away if you can press in a bushing that has that surface finish on it. And then chemical issues, usually chlorine or acids, are going to be a problematic for the nylon composite base. But we're always seeing improvements and expansions in the materials that are available. So if you go side by side and you say, well, if I look at metal, specifically steel and aluminum relative to Markforged, they're both capable of making strong parts without having to build dedicated tooling. But Markforged can build the first part and the last part completely automated. Whereas with metal, you may actually scrap a part on your first try And then as you build more and more, you get better and you can automate it a little bit more. And when you get into full production, you can be fully automated. But Markforged is automated from the first one. Metal is limited by raw material. You need to make sure you have it on hand. That's usually not a problem for most companies, but you do have to have the metal available. In Markforged, you're limited by the printer size. So you don't have to worry about the raw material as long as you have spools of material, but the printer itself limits your build size. Building parts out of metal is cheaper than making tooling to build them, but building metal parts out of Markforged is almost always going to be cheaper than building them out of metal. If you need to make it out of metal, details are going to cost more, and with Markforged parts, details are no big deal. You can add any details you want. You can put your logo on the thing. It's all good. You need something special, like a special resistance to high temperatures or some kind of a chemical. You can look at different alloys, different metals. Same thing with Markforged. There are different specialty materials to solve special challenges you may come across. Metal is always going to be heavier than a Markforged composite, in some cases significantly so, and in some cases it's so much lighter that you actually end up being able to make a part that is sort of less requirements to be so heavy and so strong. And the results are going to be really high quality every single time, from the intern to the engineering manager. Everybody's going to be able to create great parts on a Markforged printer, whereas you're not going to get those same results if you just send everybody in your office out to the weld shop and give them a shot and see how they do welding, right? So it's pretty unbelievable what these industrial composites can do. And you may be thinking, well, I don't have a $500,000 to buy a carbon fiber printer. It actually starts with the desktop series and a Mark II. You can, with a printer that's barely bigger than your all-in-one inkjet printer, you can print industrial composite parts. I use the heck out of the Mark II that I have. If you need to go a little bit bigger, or you need to go into full production, or you're looking for in-process inspection or specialty type polymers, the X7 is a fantastic model. Really ramps up by several times the capabilities of the desktop. And then the FX20 is the new breed of printer, and it's absolutely unbelievable what they can do in terms of the surface finish. These parts are absolutely pristine. You're going to be blown away when you see what the FX20 is capable of, and that's coming soon. If you, however, absolutely need metal, whether it's you want to do a hybrid part and the metal insert needs to be a special shape or whatever, you can print metal on the Metal X. The metal parts are some really cool materials, sometimes that are really hard to manufacture, things like Inconel, tool steel, copper. You can turn around parts as quick as 26 hours in many cases. You can make sparse fill metal, which means you don't have to create external topology to reduce weight, like those slots in that gear up there, or that sprocket. You could actually make that solid and then hollow it out internally, which is just mind-blowing that this capability is there. It's easy to create lots of complexity, and it's a super safe printer. It's office friendly. It's not going to smell like cutting fluid or welders, and it's not going to have any kind of hazards like you would with an unbound metal powder.